Hello, my name is Ben Holzworth, and this is my Physics 2211 Lab 2 presentation for a falling object at Georgia Tech. Quick table of contents. So in this lab, unlike the last lab, the sum of forces will not always be zero, so there will be some acceleration. This will be due to gravity. The initially we will come back to later. Unbalanced forces cause acceleration, and Newton's second law states that force equals mass times acceleration. These are formula that we will be using in this lab. Velocity update and position update just allow us to find final velocity and position with a change in t. And gravitational force is what we'll be using as the force acting on our object. And the drag force will be introduced later, but it is proportional to the squared velocity of our object. Some brief force diagrams for small change in t. So essentially the beginning of the motion. This is these are the forces acting on the object. But as t increases, these are the forces acting on the object. And so you can see initially it would be accelerating, but then once the forces become balanced, it will be at a constant velocity. And this is called terminal velocity, but we'll come back to that later. This is the observational model, and here's a brief video. That is the falling object for this lab, and this is the data from a tracker from this video plotted on a graph. As you can see, it's a negative slope because the object's y position is decreasing because it's falling, and it is almost linear. It gets more linear as it goes on, and this is because of the terminal velocity stated earlier. This is a computational model. This was without drag, so less realistic. As you can see in this model, the graph doesn't really become very linear until at the very end. It is almost much more curved, and this is because the object is accelerating the whole time because there's no drag. This is a computational model with drag considered. You can see we have an arbitrary b value. This was guessed and checked until our data aligned with the observed data. And the formula for drag force was used in the net force calculation. And as you can see, this one is very linear for some reason. It was less linear before the drag constant was changed so much. Not really sure why it doesn't look very. It should not be linear until like later on, like we talked about terminal velocity. So it should have become linear, and as you can see, it's slightly curved at the top where it's accelerating. But yes, this is a good representation of terminal velocity. As you can see, the computational model is very similar to the observed model, but just does not really reflect the acceleration very clearly. And then as far as errors or discrepancies, the object that was dropped was not ideal for this lab. It was a crumpled ball of paper, so it would have had a lot of surface area and very low mass, and therefore very, very low terminal velocity. So that's probably why the computational model was linear so fast, was because it hit terminal velocity very quickly. And there's also some initial x velocity. If you're watching the video, the ball moves slightly to the right. This may have affected how accurate this lab was, but this is a naturally occurring human error, which kind of really helped and did not really impact the purpose of this lab. Some further exploration. So terminal velocity was present most in the drag simulation, was the best way to see terminal velocity, and so that was because it took into account drag, and it was very linear looking, and that was because once an object hits terminal velocity, essentially when its drag force balances its acceleration due to gravity, it will stop accelerating and stay at a constant velocity. Yeah, just like the graph did look like for our simulation. So that was accurate. If the object had had a non-zero initial y velocity, this is the model for that. It's essentially the same, except for that if you'll see there actually isn't that little part at the beginning of the last one. If we go back, we can see this has a slight curve here because it was accelerating for a while before it hit its terminal velocity. But with a slight, or with a non-zero initial y, because like I said, the object had such a low terminal velocity, it actually hits terminal velocity almost immediately. And so therefore it is never accelerating. It's just essentially a constant velocity the entire time because of the initial velocity. So